Hi everyone, I'm Hugo from the Donders Institute in Nijmegen in the Netherlands. And I walk you quickly through this tutorial on the multiple linear regression and polynomial regression. So you should be already familiar with the linear regression model, as maybe this little recap shows us here when we have only one feature and one output. That's a simple linear relationship between input and output. And we want to build this to the multidimensional case where we might have different input features, or here labeled as x1 to xd, which can be written in the matrix form as such. And by minimizing the squared error between the estimated output y hat and the true y, we can find that the best theta parameters in that sense would be solved with this equation. So also called the least square estimates for the linear regression, because we're minimizing the squared error. So I'm going to just put this equation on the side so we can keep having a glance at it while writing our code as such. And continue on the exercise where we are using simulated data that are two-dimensional, so easier to represent graphically. And that would be the equation that we want to solve now for theta, finding the best theta parameters and see how much error we get according to the true y. So these are the generated simulated data that we're going to use. So we can see that they are two-dimensional in for x, and the output is y, and we have a little bit of noise, so they are wiggling around a plane here in this 3D space, and we want to estimate that plane, which is parameterized by theta. So to basically solve this linear regression and find our least square estimator, we're going to use this formula here. And that gives us directly the theta hat. So we remove this error and simply write our formula. So it involves the inverse of this covariance matrix, which we can directly write using NumPy formulation. So this the hat here is the dot product of the matrix multiplication between two matrices. So it simply writes as it reads pretty much. And let's see if this is correct. By running the cell, I see that I have a little error. I forgot to add here. And we get the expected output as shown here. Perfect, so we can move on and test our new learned theta parameters on the actual data and see how much error we get between the true y and our estimated y. So the code is relatively simple, and we see the mean squared error here. And there is also a utility function already implemented for us that helps us to visualize this learned parameter. So here the plane is parameterized by the theta we just estimated. And we see in all these little vertical lines, the error at the sample level for each sample, each data point, between the plane and the true data point. And this, the mean of all this error corresponds to the mean squared error here. Let's move on to the polynomial regression. So we want to be a bit more fancy, and instead of using just a linear relationship between input and output, maybe we want to use square or cubes and a polynomial expression of the input. But if you write it as such, here's the polynomial, right? In terms of x, plus a bit of noise, we see directly that this is the same equation, basically, as what we had before in the multidimensional case, where every component is simply x to a different power. So we can use the same formula to find our theta, and the only difference will be in how we represent x, the matrix input. It now will be an input that takes the for a column of ones for the bias term, then a column of x, then a column of x squared, and so on until the degree we want. That is our own design choice. So we will create such design matrix, that's how they're called, by simply following this structure where all of these are column vectors. So this is a column of ones, then we have a column of x to the power 1, so that's just x, x to the power 2, and so on until the order k. So let's implement this with the make design matrix function. So here we're looping, we first start with a column of ones, and we're gonna loop from 1 to order and add a new column, first of x, x squared, x cubed, and so on. And to incrementally add something to an existing matrix, we can use nph stack as hinted here, which allows us to horizontally stack a list of matrices. So in our case, it will look like this. We stack our previous matrix with a new column, which will be x to the power of the current degree in the loop. And let's not forget to remove the implementation error here. And also not forget to compute the simulated data that look like so. So we know that this is not a linear relationship between x and y. So maybe square or a higher degree polynomial, we will see in the next section. And now we can run our newly made make design matrix function and see if we get the expected output. Great, so we get what we wanted. We can also just test it for ourselves and maybe see if we can print, let's say I'm gonna use an order of 3 to make it easier and just use a quick array of 2, 3, 4 for x, and then I will print every columns instead of only the 2 first columns. So we can really see what's happening, and we have indeed a column of ones, then a column for x, which we can print entirely as well, 2, 3, 4, then x squared, and then x cubed, and so on. So our function seems to work well. So let's fit it for different degrees now. So we're gonna create a design matrix for each degree using the function we just created. So x and up to order. Then we also already have this function. This is simply our ordinary squared, when we can now put our new design matrix and the output y, and we will store the learned theta parameters for each order in this theta hat, the estimated theta, as a dictionary. There is already a function that has been created to plot all these learned polynomials and see it as an overlay on the existing data. So let's run this and see if we have the same kind of plot. Great. So it looks like we implemented this correctly, and we can already see that, okay, if it's only a degree or order 1 or 0, this line doesn't seem to capture quite well the variance and the fluctuation of x with respect to y, while maybe order 2, 3, or 4 seems to capture something a bit better. And we would have to compare this with a mean squared error for different order to see which order captures this best without overfitting the data. Thank you. Let's stop it here.